Today I'd like to talk about use vendor problem. Have you ever heard about use vendor problem? Where? Management. Okay. So a use vendor problem is a very basic model when you consider decision making under uncertainty. Okay. And we can use this very different form of structures with a wide range of application. So it is kind of business decision-making problem. And as you know, we would like to determine how many newspapers we need to order. Okay? We assume that we are a kind of newspaper supplier. Okay? We need to buy a certain amount of newspaper from the manufacturer, and then we can sell this newspaper to the customer or any different customers. Okay. But the thing is, demand is random. Demand is a random variable. Okay. But we assume that this demand distribution of the demand is given. Okay, and once we determine the amount of newspaper we want to order, then we are going to operate the system with the number. Go on and on. Okay, every time. Okay, so every day we need to buy a certain number of newspaper, and then we need to sell to the customer. Okay, we can come up with two different situations. First one, if we buy large number of newspapers, I mean the number is too large. Okay, then maybe we can have leftover items. Okay. If we buy small number of newspapers, in other words, too small, relative to the order of the day, okay, then we can miss the opportunity, chance to sell some of newspapers. Okay. That's the situation. And the thing is, demand is a random. Demand is a random variable. So we are going to use some notation. This Y represents number of copies of newspaper we want to order. Okay? We call this a decision variable in operations research. Okay? This Y represents number. Which number? What kind of number? Integer, right? Integer. Positive integer. 0 to infinite. Okay? But it can be any number. We can determine any number from 0 to infinite integers. Okay? We can think about this problem with two different point of views. First one, maximizing profits. Second one, minimizing cost. Okay, two different point of views. To model this problem, we are going to use some notation. Very important. And I'm going to use this notation without any specific explanation later. Large D, we usually use large capital letter for random variables. Okay, so large D represents demand of the period. Okay, this one is random variable. And Y represents quantity of the order. We can determine the number, but as long as we determine a number instead of Y, then we need to operate the system with the number. Okay. So even though we can change this value y, but as long as we determine just one number, then we need to operate this system with the number. C sub v, buying price for a single item from manufacturer. Okay. Let's say we can buy a newspaper with $1, okay, from the manufacturer, okay, publisher, okay, and then we can sell the newspaper by $2. Then this C sub P can be this number, selling price for a single item, and when we sell this single item to the customer, okay, and then C sub S represent salvage value. Whenever we have leftover items, then we need to handle them, right? One way is we can sell them with lower price to the manufacturer or different kind of organization, something like that. Okay, and usually this value, selling price C sub P, usually this one is greater than C sub V, right? Otherwise, we cannot earn money, right? If we buy a newspaper from a manufacturer in like $1 and then we sell a $0.50, then we can lose $0.50 per newspaper, right? So usually this selling price is greater than buying price, okay? And usually this salvage cost, salvage value is less than buying price. Because think about that. If this manufacturer buy these salvage items, leftover items, then this one should be less than selling price in a manufacturer's point of view, right? Okay. This one. Oh, no. Supplier means okay, to the I need to change to the customer, right? To the customer. Okay. To the customer. Thank you. There is typo. And sometimes the salvage value C sub S can be negative value. Okay. To handle leftover items, sometimes we need to pay for them, right? Sometimes. It depends on the item or situation, okay, something like that. But the thing is, this salvage value is able to be negative value. And negative value means we need to pay some amount of money to handle leftover items. Okay? And the thing is, C sub V, C sub P, C sub S, they are all constants. In the problem, as long as it is a number, then it does not change ever. Never changes. Okay? So I'd like to formulate the profit function now. Before we formulate it, I'd like to introduce one more time about the new spender problem. There is a provider or supplier or manufacturer, we can buy one item, single item, with C sub V dollar per unit, okay? And then we can set it C sub P dollar per unit to the customer, okay? If there is any leftover items, there are any leftover items, then we can handle it with salvage price C sub S dollar per unit. And in this structure, we want to sell this to the manufacturer, okay, provider. Question is, how many newspaper do we need to buy? And we need to consider profit and cost. And the most important characteristic of the problem is handling random demand. As long as demand is a deterministic value, then we don't have to consider such complicated mathematical things, okay? But now, since we are considering demand as a random number, it is quite difficult. There is some assumptions. First one, this market is stable. That means distribution of demand D, random variable, does not change as time goes on. Every day, demand follows the same distribution. Distribution name and parameter. We assume that this distribution of the random variable D does not change. Second, we know the distribution of the D, demand. Okay, that means we know the name of the distribution and the parameter of the distribution. Sometimes when you consider discrete random variable, then we know the probability that demand equals some number. Okay? And one more assumption, no emergent order or back order. In other words, back order. There is no back orders. Even though we sell the old item we have and there is more demand, we cannot do anything in that case. Okay? So let's formulate the profit function. Profit is revenue minus cost. Very, very basic formula, right? And then I'd like to introduce how to formulate cost first. As we said before, number of papers we buy from the manufacturer is denoted by Y. So how can you formulate the cost based on the structure? Cost might be C sub V times Y. Okay. Minus. Just cost. Okay. Actually, this C sub S is less than 0. Then another cost can occur, right? But for now, we consider this value is positive value. That means this one, C sub V times Y, is the only cost in this problem structure. How about the revenue? Actually, revenue is not that simple because it depends on how many paper we sold, right? But actually, demand is random. Demand represents the number of newspapers customer want today, right? Like it can be 100, 1,000, or 0, something like that. It is based on some distribution function, right? And Y, as long as we select a number, for Y. Okay. Then the number of newspapers we sold is depend on whether number of newspapers we have is greater than or less than demand. Okay, we can think about two different situations, right? First one, number of newspaper we have is greater than equal to demand. Then how many newspaper can we sell in this case? D, right? D. Okay. Number of newspapers we sold might be D if Y is greater than equal to D. Okay. And otherwise, if the number of newspapers we have is less than demand, then we can sell only Y number of newspapers. Okay. And also, we can rewrite this situation with a function called minimum function. How can you rewrite this formulation with minimum function? Minimum of Y and T. But the thing is, Y is a kind of deterministic number. As long as we determine the number, then we are going to use the number instead of Y. Okay? But large D is a random number. Okay, random variable. So this number of newspaper we sold is kind of a function of random variable. Right? Function of random variable. Okay? Sometimes we use this notation. Y, S, and D. Okay? In the reading material, the author used this notation and this notation. Okay? So you can think about that. Okay. And when we consider number of leftover newspapers, okay, we can think about the same situation, two different situations. When we compare the number of newspaper we have is greater than equal to the demand, then number of leftover newspapers might be Y minus D, right? Since we just sell D number of newspapers, but we have Y number of newspapers, so Y minus D should be the number of leftover newspapers. How about different case? I mean, if Y is less than D, then leftover 0. Okay. So we can rewrite such formulation with maximum function. Max of Y minus Dn and 0. And also we can use the different notation to represent this situation. Y minus D plus. They have the same meaning. Okay? Therefore, we can model the revenue, total revenue. Is selling price C sub P times number of newspaper we sold. So minimum of Y and D, right? Plus C sub V salvage price times number of newspaper, the leftover newspapers. So Y minus D plus, okay, sub S. Okay. And then, if we consider profit function, as I said before, profit function might be revenue minus cost. Okay. Profit function is a function of variable Y and random variable D. Decision variable Y and random variable D. In that case, profit minus cost. Then we can formulate the profit function. Okay. We can determine the number instead of Y in this problem. Okay. Let's say every day we want to buy 30 newspapers, then Y can be 30, right? Every day we want to buy 5 newspapers, then Y can be 5. Okay? And D is given. This random property and distribution of the D is given. Okay? So as long as we select this number Y, okay, and then if we consider D is a known random variable, then this function is a function of random variable. Okay. We can think about this problem with a different point of view. Okay. Just think about this problem in a vendor's point of view. Okay, our case, just our case. Then profit is actually based on C sub P minus C sub V dollar per unit. Every time we C sub So based on this vendor's point of view, we can rewrite this profit function P of Y and D is vendor's profit minus vendor's loss. Okay. In that case, this profit function might be profit per newspaper, okay, times number of newspaper we sell, okay, and then minus sub S times number of newspaper, leftover newspapers. This is exactly about vendor's point of view. The thing is, when we consider this formula and the different formula we derived just before, okay, actually they are the same. Okay, this is a kind of different form of profit function, and you can check. Okay, you can check. You can check the result of the function when y is greater than or equal to large T and y is less than y is less than t large T. Then the results are the same. Okay, this one is a different form of the profit function when we consider maximizing profit problem. Okay. And then this concept is very important concept. So this is about what we are going to be interested in later. Okay. This structure, actually this structure is has the random property, but not based on the complicated stochastic process. Random variable is the same as time goes on, right? But later we are going to talk about the situation with evolving random variables as time goes on. But we are going to think about the same measure to check the performance of the system or to make a decision based on the system. This under the random situation. In this case, the characteristic of the problem, this problem, in the stochastic process point of view, this very important characteristic of the problem is this demand does not change and profit function does not change as time goes on. This one, as long as we select y and then operate the system continuously, go on and on. Okay, this profit function is a kind of random variable, and the random property of the profit function does not change as time goes on. Okay, okay, and we are interested in expected profit in this problem. Okay, we can operate the system. We can sell this. We can operate the business and manage the business continuously with a number instead of y, and d does not change as time goes on. We exactly know the distribution of the d. Then what is the expected profit? Expected profit means it's kind of representative number of the random value. Okay, representative number. This expected value does not tell everything of the random variable, but we can recognize some very important characteristic of the random variable. For example, this expected profit is large, then good or bad? Good. This profit is very, very small, then bad, right? Bad. But we cannot say that we will exactly this amount of money every time in this structure, right? Because this one is random variable, changes every time, every day, profit changes. But if we operate this system on and on and on and on, okay, and then every day we can we can figure out the amount of money we earn, right? Let's say P of 1 represent P of Y D1. Okay, Y is a fixed number. Okay, let's assume that. Let's say we are going to buy 30 newspapers every day. Then Y is 30. Okay, and D is a random variable. So today, 45 customer visit my my store. Okay. Then this one can be observed in the system every day, and we know the distribution of the D, right? So let's say this one is I. Pi represent large P Y Di. Di is demand for the I's day. Okay. Then when we sum P1, P2, Pn up to the nth day. Okay, we can sum the profit we earn every day, and then divide by number of days. Okay. Then, if we let n go to infinite, this one converges to this expected value, because this D, random property of D, does not change. So that means this profit has a certain distribution. We don't know. Okay, but the thing is, based on strong law of large number, this expected value of profit is the same as sum of all the profit divided by n, and n goes to infinite. Okay, this value, as n increases, this value converges to true expected value. Later, the thing is, random property of this value changes when we consider the stochastic process, like discrete time Markov chain, continuous time Markov chain. Then property of the random variable changes as time goes on. Okay, but under the certain situation or assumption, this random property converges to some random variable. Okay, under a certain condition, and then this limit also converges to a certain number. We call this long run average number, not expectation in that case. Okay. This profit function, random property of the profit function does not change as time goes on. Every day, random property is the same. Okay. So this is about how to calculate the expectation of the function of random variable. But later, random property of the function changes as time goes on. But we are going to evaluate the similar representative number regarding a stochastic process. Okay? Under a certain situation, we can evaluate it. And this measure is called long run averaged measure. If we operate the system with infinite amount of time, go on and on, then how much we can earn based on the structural random property can change. Okay? That's the main difference between this Nussbender problem and the usual stochastic process problems. But I'd like to emphasize that this long run average measure is very important, and we are going to talk about different structure of the random stochastic process. But the objective of investigating such different structure of random process is evaluating this measure, long run average measure. Okay. In this case, very simple. So now we are going to focus on expected value, not just the random function p. Okay. With random function p, we are able to say not much things. Okay. Not many things. So we are going to focus on the expected value. Expected value means a kind of representative value of regarding this random variable p, function p. Now we are going to focus on this expected value, and actually this expected value is a constant as long as y is fixed. Okay, so we are going to use small p as a function of y. Okay, this one random, but this one deterministic. Okay, and we, as you said, we know that this expected value is large, then it means we can earn large amount of money, right? Good situation, right? So we want to maximize this function, p of y. That's the ultimate goal of the Nussbander problem. Later, as I said before, we are going to evaluate the similar measure called long run average measure, but we are not going to optimize the measure. Okay, this optimization is only for Nussbander problem. Okay, because we can derive the exact function of the p of y in this case. Okay. So in operations management science and operations research 1 course, at the end of the course, we discussed about how to find how to maximize a certain function, general function, right? Twice differentiable function. How to do it? Do you remember? How can we? Huh? How we can? How can you? Twice differentiable function. For twice differentiable function, how to find the local and global minimum or maximum for the function. Take KKT. Is there any constraint? No constraint. So in calculus courses, you already learned how to find it, right? Take the first order derivative, differentiate the function, and then make it equals to 0, right? Find the value y, and then check at the point second order derivative of the function is greater than 0 or less than 0. Then we can figure out local minimum or maximum, right? And then more rigorously, whenever we can check the convexity of the function, then we can guarantee the point is global minimum or maximum, right? Do you remember? So objective function can be rewritten as, okay. So in the stochastic process course or probability course, you need to be careful. Every time you rewrite the equation, you need to be careful. Okay. Okay. This small p of y is actually expected value of large p of y and t, large d, and this one can be rewritten by c sub p minus c sub v times minimum of y and t, right? Minus c sub v minus c sub s times maximum of y minus t and 0, right? Now we are going to use very basic property of expectation. Okay. This one, constant, right? Constant. This one, a function of random variable t, so another random variable minus constant times another random variable. Okay? And as you know, linearity of the expectation, this one can be rewritten by Cp minus Cv times expected value of minimum of y and t minus Cv minus Cs times expectation of y minus large t plus. Okay, so from here to here we used linearity of expectation. Okay, so every time you rewrite the equation, okay, you need to be careful why this is true. So now to calculate the function p of y, okay, as long as so c sub p, c sub v, c sub s, they are given number, and as long as we can calculate this expectation and this expectation, then we can calculate the expected profit in this problem. And as you can see, the homework 1, I think you already have some experience to calculate such expectation, right? Otherwise, please work on it, check, okay? So we can think about two different examples. Okay. Before that, we are going to do two different things. First one, we want to find expected value of minimum of y and d and expected value of maximum of 0 and y minus d when the distribution of d is given. Okay? And then the ultimate goal is we want to maximize the function p of y regarding y. What kind of value y can make this function be the maximum value? Okay?